begin by recapping what we have done so far, which is actually quite a lot. In the very first episode, we talked about types of switches, simple circuits. We built a continuity tester and talked about basic soldering. I told the whole internet about my favorite lead-free alloy and the soldering iron that I have been using. Which is convenient because it can be powered using a LiPo battery pack. This is helpful because then you can solder in locations where you don't have AC power available. For example, if you're building a solar power system, which is, for a 12-volt off-grid system, surprisingly cheap and easy to do. In fact, that should be the sort of thing that this course correctly prepares you for. As far as paper notes go, we began with a simple circuit, a continuity tester, which I keep putting on the desk and taking back. Very exciting. Now, after that, we talked about Ohm's law, the hydraulic analogy for electrical current, and why they use high voltage for power transmission lines. Then we introduced semiconductors, talked about P and N-type semiconductors. P-type have atoms that have fewer than 4 valence electrons and create movable holes, which actually move about by the next electron filling in the hole and the next electron filling in that one, but it acts like a positive charge carrier. N-type semiconductor has an atom, such as phosphorus, that has more valence electrons than silicon's 4. The substrate doesn't necessarily need to be silicon. It used to be germanium. Currently, it's mostly silicon. Silicon carbide is used for some power transistors, and there is talk of using synthetic diamond. We're basically moving up that column on the periodic table. We measured the forward voltage drop of different LEDs. We found that bluer LEDs, which have more energy per photon, take more volts to turn on. This is because the band gap of the semiconductor material used to make the LED is larger. Then we introduced capacitors. These are 2 plates with a narrow gap between them that are capable of storing electric charge. Talked about capacitors more, how you could use a diode as a capacitor, and gave equations for capacitor charging and discharging. There are equations like this for an inductor, but they don't come up as often, so I glossed over them in my description of inductors, which are basically electromagnets. Wrap 2 of them around the same core, you get a transformer. We talked more about the hydraulic analogy and how a battery would be a pump, a resistor would be a flow restriction, an inductor would be a weighted impeller that can spin freely, and a capacitor would be this large tank thing with a flexible membrane in the middle. I think we did this earlier. We talked about how the peak voltage of AC voltage is square root of 2 times the RMS, or root mean square voltage. In the United States, you'll see 120 volts RMS, which means the actual peak voltage is about 170 volts. It's a tiny bit less. It gets to be a long decimal. We talked about how transformers are capable of converting one voltage to another voltage depending on the ratio of turns between the 2 coils. Note that you can make a transformer with 1-to-1 ratio, which simply passes the voltage through unchanged. This is called an isolation transformer. It is useful if you are working on line-powered equipment and you do not want to get a potentially lethal electric shock. Then we talked about diode bridges, how you can structure diodes in this diamond shape, and they will make it so that current always flows the same direction through the load. This can be used in combination with the transformer to convert wall power down to a lower pulsing AC voltage, which, through the action of the diode bridge, then creates this pulsing DC voltage, and combined with the filtering effect of a capacitor, enables you to get a constant, relatively constant voltage output. There is some ripple as the capacitor charges and discharges. I showed a practical example of this circuit in living Technicolor, which would take a wall voltage input, use these 4 diodes in this capacitor to convert it to a pulsing DC current. It was originally inside of this case, dear viewer, with these ratings. Unfortunately, the process of disassembling it broke it. Very tragic. We thank it for its service to educating you, dear viewer. Then we introduced junction field effect transistors, which work by controlling the thickness of a depletion region and using one of the P or N regions in a diode as a long conductor, such that current will flow here normally, but if you apply a reverse voltage, then the depletion region pinches off the current flow, called cutoff. We demonstrated that circuit in real life. And you can see that altering the voltage applied changes how much current flows. Then finally, we introduced the MOSFET, the depletion mode MOSFET acting much like the JFET, and the enhancement mode MOSFET working by having a structure such as this one, where you have an N-doped region, a bulk P-doped region, and another N-doped region. Applying a positive charge here repels the holes away from the area under the gate and attracts minority carriers, electrons, which are still present in P-type silicon, converting a thin layer effectively to N-type, which creates a conductive channel between these two little islands, the thickness of which can be controlled by varying the gate voltage. That is this lovely circuit here on the bottom, which I can turn on or off by allowing a small charge to flow through me to the gate layer. If this is too fast of a recap for you, dear viewer, fear not. For the entire series now has a runtime longer than Titanic. I have not yet introduced the bipolar junction transistor, which I would like to do before we get to our first actual practical project. I'm sure you are just thrilled by this. So, the 2 types of transistor we discussed previously, the JFET and the MOSFET, they are both voltage-operated devices, by which I mean you control the voltage at a gate and it controls the thickness of a depletion region in the case of the JFET or the depletion mode MOSFET, or it effectively creates a new channel of either N or P-type semiconductor from the opposite type, depending on the applied voltage. Either way, you're controlling the thickness of a conductive channel with an applied voltage. This last type of transistor that I will be introducing controls a current with another current instead of controlling a current with a voltage. It's called the bipolar junction transistor. It is not the only other type of transistor. There are many, many different types of transistors. These are simply the most common ones and comprised the minimum that I thought would be needed in order for you to be able to really sink your teeth into some practical projects. without having each one come up with too much previously unknown material. So, bipolar junction transistor is a 3-layer device. That works by minority carrier injection. The middle layer, called the base, is thinner than the other 2 layers. I'm going to start by describing an NPN transistor, an NPN bipolar junction transistor. This transistor, see, we're not getting a very good angle of these pretty pictures. Maybe I can set you on my oscilloscope, dear viewer. From my perspective, you are comparatively small and flat. Have to be held at just the right angle. That might be a little low. But let's see how that works for now. So, here's a happy little NPN transistor. It has 3 terminals. This is its symbol. This is how it is actually built in silicon. This is the collector. This is the base. This is the emitter. In terms of conventional current, this transistor takes some current flow this direction. Let us call it X, and allows some multiple of that current to flow this direction. The factor that it multiplies by is called beta, or, for fun, in many data sheets, HFE, with the FE as a subscript. The H I have seen both upper and lowercase, so good luck. I prefer the term beta because Greek letters look fancy. Now, how does it achieve this? So, let's add some batteries to our pretty little picture. If you built this circuit in real life because there are no current limiting resistors, you would simply burn out your transistor. You'd be very sad. So, this is for illustrative purposes only, dear viewer. I'm going to get in the habit of marking ground terminals. Does it really matter? Kind of. Once you're using simulation software like the falstad circuit simulator or LTspice or some other software package, they tend to get unhappy unless you specify a ground point somewhere in the circuit. So without this voltage being applied, there is a reverse biased PN junction here that does not conduct. So current cannot flow through the transistor as a whole. It's very sad because this depletion region here prevents conduction. However, there is still an electric field present across the depletion region. This is important to note, dear viewer. I'm sure you are at the edge of your seats. Now, if you apply an input current to the base, which in reality can be considered sucking electrons the opposite direction, you end up filling this thin base region with extra electrons because these extra electrons are right up next to this electric field, they tend to get sucked across instead of making it all the way out to this terminal. And for a common transistor, this is really an oversimplification, but this whole beginning has been, and it is already very long, you can assume that beta is 100. That is, for every electron that makes it actually to the base terminal, 100 of them get sucked from the emitter to the collector. They're named that because this end emits the electrons, this end collects them. So the long and short of it is that a bipolar junction transistor multiplies the current through the base by 100. Now, it doesn't multiply in the sense of generating it. Better wording would be whatever current you apply to the base, the transistor will allow 100 times that current to flow from the collector to the emitter. These arrows are conventional current, which is assumed to be the flow of positive charge carriers from plus to minus. Otherwise, this arrow would be backwards, and all of these schematics would be somewhat harder to read. Now, we may demonstrate our new friend, the bipolar junction transistor, or BJT. So, we can now unplug our previous experiments, as we have extracted all of the knowledge therein for the time being, though there will always be more. There is no shortage of things to learn. There is a shortage of time in existence overall. In fact, there might be more things to learn than overall time in existence. Isn't that funny? So I need to be able to measure currents to do this. So I will be using my friend the multimeter. And the DC amps measuring region. What fun. But I need to measure this current on a breadboard. This connection looks a bit insecure to me. But let's see how it works. So, there are, of course, a wide variety of transistors available. I'm going to demonstrate with the MPS A06 NPN transistor. This transistor has a typical gain of about 200. You should bear in mind that the beta or gain or HFE, which are all synonyms, that factor of a transistor is highly variable. In fact, I can just pull up the data sheet. Oh boy, data sheets, say the viewers. We sure love data sheets. Yes, do we ever? Do we ever? So the gain of this transistor will be highly variable. DC current gain, which is listed here as HFE with a lowercase h. They don't even specify the maximum. They say minimum 100. Maximum, maybe 200, maybe 500. This is because controlling the thickness of that gate layer that is very thin is actually kind of tricky. But the upshot of that is that we have no idea what the multiplication factor of the current will be. So designing your circuit around that is a bad idea. If you design your circuit expecting a constant beta, then it'll be unreliable. It'll only work for the specific parts that you tested it with. And then you'll start to get strange errors when you try and use it with other parts. Now I need a large, high-value resistor. Mega ohm should do it. 1,000,000 ohms. And I should draw a lovely schematic for you. You can tell based on the size that these are 1/4 watt resistors. That will go to the base. I need another piece of wire to connect the emitter to ground. And then I should be ready to actually measure the current flow into the base with 1 meter and the current flow out of the base, into the collector with another meter. One on the right is measuring current flow into the collector, and then the second meter will measure current flow into the base. Because the base current will be much smaller, this meter is set to the 200 microamp scale. Now we need to apply power to our circuit. And then use this lower meter itself to connect between the plus connection and this end of the resistor. Then we should get some actual numbers. Or fun troubleshooting an open circuit somewhere. One of the two. Okay. Is this circuit getting power? No. Why not? The negative input terminal isn't connected. That would explain why it is not doing what it would otherwise be expected to do. Did you know that you have to apply power to your circuits for them to work? This may shock you. Try to find an angle where I'm not obstructing your view. All right, so 8.0 microamps in, 1.3 milliamps out, because these are set to different values. This showed a negative number because I connected it backwards. Not intentionally. In this case, it doesn't matter, we just remember that we can take the absolute value of that number to get the correct amount. So, now we can draw the schematic of what we were doing, which is always a good idea. like all of our work so far, it starts with this lovely 9-volt battery. Then we ran it through a meter, which is a circle with either an A or a V in it. A is for an ammeter, which we were using, and then V is for measuring voltage. So we ran it through a milliammeter. Then we had an MPS A06 NPN bipolar junction transistor. And that was just connected straight back to ground, which, again, you should not do in a practical circuit. The reason this doesn't burn out the transistor is because this resistor is big enough. Until you feel comfortable guessing at correct resistor sizes, include guard resistors in line with your components so you don't burn anything out. Then there was a second microammeter. I think for the standard drawing it would just be a circle with an A. The mu is, I think, non-standard, but people would tend to know what it means, I hope. So what we found is that the current flow here was 1.3 milliamps, and the current flow here into the base was 8 microamps. From this we can calculate the beta, the DC current gain of the transistor. Beta equals the collector current divided by the base current, which in this example is 0.0013 amps divided by 0.000008 amps. Exciting, no? Which can be calculated to give us an actual numerical value of 162.5. Now the minimum value is 100. 162.5 is in fact larger than 100. And then another thing to note is that many multimeters have a transistor test mode built into them. So you can just plug the transistor directly in, set the multimeter to HFE, and then you'll be able to tell the transistor's values. So you plug the transistor into the meter, making sure to respect where the emitter, base, and collector are connected. Set the meter to measure gain. Have I got this backwards? Yes, I do. That's nice. So this meter claims the transistor has a gain of 186, and the calculated value was 162.5. I'm pretty sure that the meter is testing the transistor under more ideal circumstances than our circuit was. Also, I'm not sure how accurate my ammeters are. These are, like everything else, from the lowest bidder. In any case, The numbers are close enough. And it's a shame they don't give maximum values. Usually you see 100 to 200, 100 to 500. But in any case, this has been your preliminary introduction to the bipolar junction transistor.